It's my pleasure to welcome Mike Crommie. And I think basically I wouldn't have to give an introduction to this audience, but in case there's somebody who hasn't heard who he is, let me very briefly introduce him. So after graduating with a PhD from UC Berkeley, Mike Crommie was a postdoc at the IBM Almaden Research Lab. And I think most of you are aware of these beautiful results, iconic results on quantum corals from his time with Don Eichler. And I was actually checking this out today, and I was very surprised to find out that this is not the most cited paper from him. There's some much later work on bilayer graphene that is cited more than the quantum coral stuff. But still, I think in the field, this is one of the most iconic results. Okay, anyway, after his postdoc, he first became an assistant professor in Boston University, and then moved back to UC Berkeley, 99 as an associate professor, and has been there ever since. Now, of course, as a full professor for quite some time. The Crommie group, I think, if you look at the stuff coming out over the years, they've had a very broad research profile, looking at the variety of different topics. And I think the common points are that it's mostly scanning probe microscopy in one form or another. And the other common point is that the level of science has always been extremely high. I think I'm not going to go into details, but over the years, there's been sort of landmark experiments on, for example, molecules, molecular self-assembly, molecular materials, graphene nanostructures, on-surface synthesis, graphene nanoribbons, including sort of nanoribbon heterostructures and topological states in these GNRs. And in the recent few years, also extremely nice results coming out in 2D materials, in TMDs, niobium diselenide, tungsten diselenide, tantalum diselenide. And I think today we'll hear more about the last one. So the title of today's talk is Imaging Spinons in 2D Gapless Quantum Spin Liquid. And I think with that, I look forward to your talk a lot, Mike. So please, the floor is yours.
Excellent. Thank you, Peter. Hello, everybody, and please let me know if there's any issues with the audio. So today I'll be talking about imaging quantum spin liquid behavior in single layer 1T TaSe2 tantalum diselenide. So here's an outline for my talk. First, I'll say some introductory words about quantum spin liquids. Oh, by the way, can you see my cursor as I move it around? Do you see it?
Yep.
Yes.
Okay, great. Thanks. Okay. So first, I'll say some introduction about quantum spin liquids, and then I will talk about how single layer 1T TaSe2 satisfies the requirements of a quantum spin liquid, which is that it has a frustrated lattice, it's a bond insulator, and it has local magnetic moments. Then I'll talk about how we're able to observe quantum spin liquid behavior in single layer 1T TaSe2 through the observation of long wavelength modulations, which we can explain as a result of Spinon Fermi surface instability, which leads to Spinon quantum interference. Okay, so what is a quantum spin liquid? That's sort of a main topic in this talk. Well, a key ingredient to quantum spin liquids is that you need a highly frustrated spin lattice. And so if you have a bunch of spins that are interacting with each other via Heisenberg Hamiltonian, as you see here, where J is positive, and so you get antiferromagnetic interactions, then if you put them on a triangle, then you can see how that third spin doesn't know which way to point. That's frustration. And so there are some famous lattices that give you spin frustration, such as the triangular lattice, the Kagome lattice, which classically give you a lot of low-lying magnetic states. And quantum mechanically, they can lead to interesting behavior too, such as quantum spin liquid behavior. So one of the characteristics of quantum spin liquids is that they are highly entangled states. And sort of to see that, I think it's useful to first consider what is not a quantum spin liquid. So this state is not a quantum spin liquid. This is the Néel state. It's a 120-degree rotated antiferromagnetic state. And it's not a quantum spin liquid because first it has magnetic order, and you can see how you can write this as a simple product state of the wave function of all the different spins. So it's not entangled. And also you can see that the net spin, the average spin at any one lattice site is not zero. And so that means it's not a quantum spin liquid. But let's consider a different state, the resonating valence bond state of Phil Anderson that Phil Anderson came up with in the early 70s. in this state is a quantum spin liquid. And this state, in this state, you couple the spins into singlet pairs throughout the lattice, and then you write the state as a sum of all the different configurations of singlet states, as I show in the cartoon. And this is a highly entangled state because you cannot write it as a simple product state. There's no magnetic order. And if I look at the average spin at any one lattice site, then the average, it fluctuates and the average is 0. So those are qualities of a quantum spin liquid. Another property of a quantum spin liquid is that you get charge fractionalization. And what that means is that if I stick an electron into a quantum spin liquid, then it's going to break apart into a neutral spinon and a spinless charge-on. And you can see that here in this cartoon. This is the spinon, and this is the charge-on. And a way to see that using a simple cartoon is, let's consider this resonating valence bond state here on the left. And if I pluck out an electron that leaves behind a positive hole, a neutral spin-on here, and you can see how by rearranging the bonds of the singlets, you can see how this holon and the spin-on can kind of start moving around. And so the spin-on and so they separate from each other. And that sort of gives you a sense of how charge and spin can separate in a quantum spin liquid. Without a bunch of fancy equations. And so people have been studying quantum spin liquids in different materials for a number of years. There's a bunch of different materials where people claim to have seen it. Here I show them in this column on this table. And there's a bunch of different behaviors, a bunch of different lattices, such as people claim to see quantum spin liquids on the triangular lattice, the Kagome lattice, the honeycomb lattice, the pyrochlore lattice. They claim to see gapless quantum spin liquids, gapped quantum spin liquids, chiral quantum spin liquids. But today I just want to focus on one type, and that is this type. I want to talk about spin liquids living on a triangular lattice that have U1 gauge symmetry and that result in a gapless spin-on Fermi surface. And so let's take a closer look at this. And so where would such a quantum spin liquid arise from? So a way to think about it is first consider a triangular lattice and fill it half filled with electrons, 1 electron per site. And then we can model the electronic structure using the Hubbard model, where here T is the hopping amplitude for an electron to hop from site to site, and U is the Coulomb repulsion. It's the energy of double occupancy. And so if you're describing the behavior with this Hubbard model, then in the limit where U is really big, where there's a lot of Coulomb repulsion between the electrons, then you get a Mott insulator. And the Hubbard model can reduce approximately to this simple Heisenberg model. The electrons cannot move anywhere, they're stuck, but the spins can rotate around. And here, the ground state is actually Néel order. It's this 120-degree rotated antiferromagnetic state. And so that is not a quantum spin liquid. However, if the Mott insulator is not so strong, if the U is a little bit smaller, then you start getting other terms in the Hamiltonian. You start getting other interactions, such as this ring interaction I'm showing here. So this is an interaction between 4 adjacent spins. And so you can look up here, see those 4 guys right there. They can interact via this ring interaction term, and that provides additional frustration, which then can, under some circumstances, cause the ground state to not be the ordered state, but to be a quantum spin liquid. And you can think of how these ring interactions are not very intuitive to me, at least. But if the gap gets smaller, you can think of them as terms in a perturbation expansion. So if you have so people have thought about quantum spin liquids on a triangular lattice, and one of the predictions is that you get the charge fractionalization that I mentioned before. You have spinless charge-ons and neutral spin-ons. For the undoped material, there are no charge-ons because they're gapped out by the Mott gap. So there's no charge-ons anywhere. But there are spin-ons. The neutral spin-ons are free to move around, and they move around like free electrons. And because they're fermions, they fill up the spin-on band up to a highest energy, the Fermi energy, and they form a Fermi surface in the Brillouin zone, as you see here. And this is the familiar Brillouin zone that you expect from a triangular lattice. These are the reciprocal lattice vectors of the triangular lattice. And so it should remind you a lot of what you would get for a free electron gas. The spin-ons are like a metal inside of this Mott insulator, but they have no charge. So it's a really kind of strange object. And so they have no charge, they're neutral, but there is but there is sort of a subtle thing that happens, which is important because of the gauge symmetry of this system. The spinons have a gauge charge, so they can actually feel each other as though they were charged. And that's we call that's an emergent behavior. They can feel a gauge interaction between each other. So that means that one spinon creates a gauge field that the other spinon can feel. So if that spinon is moving, it would create a magnetic field, just like that the other one would feel, just like normal Maxwell equations. But this is something that we cannot feel outside of the quantum spin liquid. It's happening inside. And to us, the spinons are neutral, and we cannot grab onto them with external electric fields. Okay, so how do you observe this? So this is kind of strange behavior that a quantum spin liquid has, and how do you observe it? Well, you can't use, it's hard to use conventional transport properties such as conductivity, but you can use thermal experiments such as heat capacity and thermal conductivity, in which case you expect the quantum spin liquid to exhibit metallic behavior, even though it's an insulator. And people have seen this, as I show here. Also, you can use neutrons because you can do inelastic scattering of neutrons and get signatures of the spinons, as people have done. But it's hard to map the spinon Fermi surface. It's hard to actually measure the Fermi wave vector because we cannot do our normal tricks like de Haas van Alphen and Shubnikov de Haas. We cannot do those things because the spinons are neutral. So today I want to talk about a different way that we can measure the spinon Fermi surface, and that's using scanning tunneling microscopy. And to understand that, let's consider how STM works for a conventional material. For a conventional material, the rate at which electrons tunnel from the STM tip into the material is proportional to the wave function of the electrons at the surface of the material. That's just the familiar Tirsoff-Hammond interpretation that we all know and love, at least all STM people know and love it. But something a little different happens for quantum spin liquid, because for a quantum spin liquid, when you tunnel an electron into the quantum spin liquid, the electron has to break apart. It fractionalizes into a charge-on and a spin-on. And so the rate at which the electrons tunnel is going to be proportional to the product of the spin-on wave function times the charge-on wave function, because both of these things have to happen at the same time. And so probabilistically, that we have to get the rate is going to be proportional to this product. So that means that we should be able to see the spin-on wave function by measuring the tunnel current of the STM. It's just right there. So why aren't there a bunch of STM papers out there where where all the STM guys are saying, I can see spin-ons? The reason, of course, is because quantum spin liquids live in Mott insulators, and you cannot tunnel into an insulator. You need a conducting surface to do STM. But with two-dimensional materials, and so normally that's impossible, but with two-dimensional materials, we can do a trick. The trick we can do with 2D materials is if we put the 2D material on a conductor, then we can tunnel into it in principle. The electrons can fractionalize into spinons and charge-ons, but then we can drain the current out through the conductor. And so in principle, we could image then the quantum spin liquid in this situation. But that two-dimensional material has to be very special. It has to satisfy certain criteria to be a quantum spin liquid. For example, we need a frustrated lattice. We need to be a Mott insulator. We need localized spins. So those are some stringent constraints. And so now I want to talk about a material that we believe satisfies all those constraints. And this material is single layer 1T TaSe2, tantalum diselenide. This is a transition metal dichalcogonide. And when you look at it from on top, this is what you see. The purple balls are tantalum, the green balls are selenium. And when you look at it from the side, it has this familiar TMD structure. It's a tri-layer. The tantalum atoms are in the middle, and on the top and bottom, you get selenium atoms. This tantalum atom has just one d electron. So it's really nice and simple, just one d electron per tantalum atom. There is a nuance here, which is that this material has a charge density wave, a Star of David charge density wave. This is driven by electron-phonon interactions. You can actually derive this CDW using density functional theory. And the CDW is what determines the lattice symmetry of this two-dimensional material. And you can see that it's a triangular lattice. So you can just see it. The CDW is sitting on a triangular lattice. So that gives us a frustrated lattice. So that's nice. That satisfies the first criteria. But what about the Mott insulating criteria? Is it a Mott insulator? Well, that question is actually not so obvious to answer, because people have studied this material in bulk a lot since the 70s. And what people have seen is that bulk 1T-TSC2 is a metal. You can see that from the resistance versus temperature right here. It's a metal. However, surface science people have looked at it. And if you look at the surface of 1T-TSC2 by STM or ARPAs, then you can see insulating behavior. And so some people claim that it's a Mott insulator on the surface, but it's bulk metallic in the bulk. And it's kind of complicated. And what makes it complicated is the interlayer coupling. That's what sort of screws it all up, in my opinion, because it's just become so complicated. And also, I should also mention the sister material of 1T-TSC2, which is 1T-TAS2, salt, where you have sulfur instead of selenium. This is an even more famous material than TASC2, and it's been studied a lot. And this material in bulk is an insulator, and people have studied it for many years and claim that it's a Mott insulator. Here you can see some STM measurements from a group. I think this is Yayu Wang's group, and you have the lower Hubbard band and the upper Hubbard band. And this material, TAS2, has been predicted to be a quantum spin liquid by Patrick Lee and coworkers a few years ago. And in fact, experimentalists have seen evidence for gapless quantum spin liquid in this material. But some people have also seen evidence that go against the quantum spin liquid interpretation. And once again, the situation is complicated by the interlayer coupling, which really, in my opinion, makes things quite complicated in these materials. And so the obvious thing to do, or at least one obvious thing to do, is to get rid of the interlayer coupling to try to make it a simpler kind of situation. And so that's the path that we decided to go down. And so we got rid of the interlayer coupling by just looking at this material at the single layer. And to get the single layer material, we use molecular beam epitaxy. And so the way that we grew the material was, the material was grown by our collaborators, Sung Kwan Mo and Ziek Shen. Ziek Shen is a professor at Stanford, and Sung Kwan Mo runs a group at the Advanced Light Source at Lawrence Berkeley National Laboratory. And these guys grew the materials in a collaboration with us, and they gave my group the materials. And the way they grew them was they took silicon carbide wafers, they heated them up in UHV, then they grew the bilayer graphene, and then they used MBE to grow the single layers of 1T-TSC2 on top. And then they gave the samples to my group. And in my group, what we did was we looked at them with STM. And here you see a typical STM image. The bilayer graphene is the dark blue on the bottom. The single layer 1T-TSC2 is here. And in the middle here, you see a bilayer of bilayer of TSC2. And if you zoom in on the single layer region, then you see this, this is the CDW pattern. You see it very nicely. Each of these blobs that you see is a single Star of David with 13 tantalum atoms inside of it. And it's sometimes hard to see the atoms with STM, but if you do a carbon monoxide tip non-contact AFM, then you can see the atoms just fine, which we did. Here you can see it. What you're seeing here is the selenium atoms on top, and if you count them, you get the right counting. So when we did we did STM spectroscopy on the single layer 1T-TSC2, and this is what we saw. And as you can see, it's an insulator. You see there's a gap at zero, the Fermi, this would be the Fermi energy, and there's a gap there, and the gap is on the order of 100 millivolts. And so that's good. It's an insulator, yay. But what kind of insulator is it? Is it a band insulator or a Mott insulator? And once again, it's not completely obvious. So what we can do is we can take a closer look at the system. And so let's just do some counting. If we look at the unit cell of this material, we see that this is the unit cell. It's the CDW Star of David. It's a unit cell. There are 13 atoms in it. 13 tantalum atoms. Each tantalum atom has one d electron, and so that means there's 13 electrons per unit cell. Now that's an odd number, and so by basic solid-state physics reasoning, we expect this material to be a metal, not an insulator. And so if we do DFT calculation on this material, sure enough, we get a metal. And here I show the DFT band structure calculated by our theoretical collaborators, Stephen Louis, his group, and also Amy Liu's group. And the way to interpret this band structure is first look at these atoms around the periphery of the Star of David. There are 12 atoms in the periphery. Those 12 atoms have 12 electrons. Now those 12 electrons are going to fill up 6 bands. And those are these bands here in this band structure spaghetti. There are 6 tantalum bands. So all those electrons fill up those bands. And so they're not so important. But the most important one is that guy in the middle. that guy in the middle, his electron goes into this flat band here. And since there's one electron from the guy in the middle per unit cell, this flat band is only half filled, and that's why it's a metal. But if you take a closer look at it, then you'll realize that that's a pretty flat band. And if we look at the width of that band from DFT, it's on the order of only 20 millivolts. Whereas electrons sitting inside of that flat band are going to have a Coulomb repulsion. They're gonna push against each other with an energy on the order of 2 volts. So that means that the ratio of the bandwidth to the U is really small. It's on the order of like 1/100. And so that means that this material is well inside of the Mott insulator regime. We expect it to be a Mott insulator. But the problem is that it's really hard for us to model a Mott insulator using ab initio technique. So it's hard to compare our STM to calculations because there is no theory. There is no ab initio theory for Mott insulators. It doesn't exist yet. Although maybe that's a controversial statement, but that's sort of my opinion. And so we have to compromise. And so the compromise that we made is to use DFT plus U. So what we do is we to approximate the behavior of this material, we add a U to the DFT, 2 electron volts at the site of each tantalum atom. Our theoretical colleagues did this. And when you do that and calculate the electronic structure, then a gap opens up. And sure enough, it turns into a Mott insulator. We have an upper Hubbard band and a lower Hubbard band and an energy gap. This is the DFT plus U band structure. And if you calculate the density of states, then this is what it looks like here on the bottom. And you can see it actually looks a lot like what we measured experimentally. There's a really pretty strong resemblance between the theory on the bottom and the STS. We get a nice gap. Some of the features look quite similar. And if we look at the orbital texture from the theory, we see that it matches our STM pretty good over a certain energy range. Here on the bottom, I show the theory results of DFT plus U. Here on the top, I show our STM data. These are DIDV maps on the upper right. And you can see here in the field states, the theory says that we should get blobby LDOS in the center in a Star of David. And sure enough, experimentally, that's what we see. If we go to high energy, we see more complicated orbital texture. And the DFT plus U models that pretty well. Look here on the bottom, it looks a lot like our data. If we start going down in energy, the orbital texture changes, and the DFT plus U captures it pretty well. As we go even at further energy, it's working. But then when we go into the upper Hubbard band, it no longer works. Boom, here we are in the upper Hubbard band. You can see how the experiment on top looks quite different from the theory on the bottom. In the experiment, we have a depletion of LDOS at the center of the Star of David, whereas in the theory, we get a lot of LDOS there. And this is not so surprising because what we have is a Mott insulator, so we don't really expect the DFT plus U to really model all the behavior. And then if we go, yeah.
Mike, sorry, there's a question by Vidya. Vidya, please go ahead.
Oh yeah.
Mike, just very briefly, why is the DFT? Why is the position of the Fermi energy in the DFT calculation so close to the lower Hubbard band? I mean, I'm noticing if you go to the previous slide, yeah, here, so no, that one, the next slide. You have the position of the lower Hubbard band at 330 millivolts below the Fermi energy. In the DFT calculation, I'm curious, what sets the position of the Fermi energy with respect to these bands? Because I would have thought the Fermi energy should be in the middle of the Mott gap. Why is it so close to the top of the lower Hubbard band? That's my question. In the theory.
Well, that's a good question. Let me think about that for a second. I mean, here when I look at the band structure, the 0 is pretty close to the middle.
Yeah.
I'm wondering if when they did, when they calculate the density of states, they often do a Gaussian broadening. I'm wondering if the Gaussian broadening for all of these bands gave a stronger weight to this bottom part in the Gaussian broadening. I'm not exactly sure. And I'm not exactly sure exactly where this 0, I know that, when DFT guys calculate insulators, sometimes it's tricky where the 0 is. I'm not sure whether they're doing it arbitrarily or maybe it's because of the work function. Yeah. So I guess I'm not exactly sure, Vidya.
Okay, thanks.
Okay. Okay, and so we see that when we put the energy in the upper Hubbard band, then the experiment and the calculation are quite different, and that's to be expected because we have a strongly correlated Mott insulator, and so we don't expect DFT plus U to capture everything. And when we go to slightly higher energies, we see that we also get very poor agreement between the experiment on top and the theory on bottom, because now we see that there's some LDOS in the middle, whereas the theory says that there shouldn't be. And what we think is happening here is that there's an electron in the field states. There's an electron sitting here in the center, and we believe that the correlation of the Coulomb repulsion of that electron is pushing state density from the middle to higher energy. So we're getting some shifting of the spectral density of the upper Hubbard band up to slightly higher energies. And so the bottom line of all of this is that for the 1T TSC2, we do get a frustrated lattice and we get Mott insulating behavior, but it is not a completely generic Mott insulator. So the next question is, do we see localized spins? If you have a Mott insulator, you expect localized spins, but it would be nice to see them just to be sure. And so we decided to use the Kondo effect to see if there's localized spins. And I'll remind you what the Kondo effect is. The Kondo effect is what you get when you have a localized magnetic moment sitting on top of a metal. Then you get an exchange coupling between the spin of the local moment, which couples to the spin of the itinerant electrons. And if you go to low enough temperature, then that causes a Kondo singlet to form, which screens the spin of the local moment. And we saw this a long time ago in this data that I'm showing you, because in 1998, because the signature of the Kondo singlet is a narrow resonance in the local density of states at the Fermi energy. Here you see the resonance. The first person to see this for a single atom was Vidya Madhavan, and this is her data from 1998. And so if you think about that, then you can think, well, what happens if I put a Mott insulator on top of a metal? Well, the Mott insulator should be just a collection of spins. And so if the Kondo coupling between these spins is stronger than the exchange coupling, if the Kondo coupling between the spins and the itinerant electrons is stronger than the exchange coupling between the spins in the layer, then we expect Kondo to win, and all these spins are going to get screened by the conduction electrons like that. And so this intuitive picture is actually borne out by more hardcore calculations. For example, this is the result of a dynamical mean field theory calculation by Helms and coworkers, where they calculated what happens when you, at the interface of a Mott insulator and a metal, when you're inside of the metal, you get this continuous density of states, this black line, and as you go into the Mott insulator, you see this Kondo resonance, and as you go deeper into the Mott insulator, then you get the Mott gap. And so this is precisely the picture that I just explained to you intuitively. And so we thought we would use this technique to see if we could actually observe the spins in our Mott insulator. And so we took the 1T TSC2 and we stuck it on top of a single layer of 1H TASC2, because 1H TASC2 is a good metal. Now you might ask, why didn't we just stick it on the graphene, which we did do, and why didn't we see the Kondo there? And the reason is because the density of states of bilayer graphene is small, whereas the density of states of 1H TSC2 is really big. So we can then see the Kondo effect better. So here's the data. This is the kind of surface you get. You can get this under certain growth conditions. And so here we see the 1T TSC2 single layer, 1H TASC2 single layer, and here is a single layer of the 1T phase sitting on top of the 1H phase. That's the one we want. And if we look at the 1H phase with the STM, we see metallic behavior. This is a nice metallic density of states. There's a little dip there, but it's a nice metallic density of states. And we published a paper on that a couple of years ago in the lower left. And then if you go on the 1T TSC2, then that's what you see, and you see that nice Mott insulating behavior I was just describing, and we published a paper on that this year. But now if you go on the 1T layer on top of the 1H, you see something funny, because if you look at the high energy behavior in the filled states and the empty states, you see similar behavior as the other materials. But when you go to the low energy behavior, you see completely different behavior. Now we see a Kondo resonance. Now we see a peak. And so if we look at that Kondo resonance, we see that it exists everywhere on the surface. All the stars of David show that Kondo resonance. And to try to verify that this is Kondo behavior, we measured the temperature dependence of that peak. We warmed it up because it turns out that if you have a Kondo resonance, then you expect a certain kind of, you expect the width to widen with temperature. And that's something that we saw many years ago, back in 2002. And a lot of people have seen it since then. And so we use this as a test, because as we warmed it up, we see that the Kondo resonance broadens, and it follows this very specific functional behavior that I show here in this little formula. And if this was not a Kondo resonance, then we would expect this to just be a straight line, because this is the width after thermal deconvolution. So this is nice Kondo behavior. And so that's a signature of the spins living inside of these of the Mott insulator. So this is quite nice, because this is telling us that now we have a frustrated lattice, we have Mott insulating behavior, and we have localized spins. So now we're ready to look for quantum spin liquid behavior in 1T TSE2. So what we do is we put it back onto the graphene, as you see here, and we start, and what we do is we do very careful DIDV maps of the 1T TSE2 surface when it's on the graphene. And when we do these DIDV maps at high energy, far away from the Hubbard band edges, deep into the filled states or deep into the empty states, this is what we see. What we see is the CDW, which we know is there. And when we do a Fourier transform of these maps, all we see is the CDW reciprocal lattice vectors. That's what these 6 peaks are in the Fourier transform. Over here, it's just the CDW triangular lattice reciprocal lattice vectors. There's nothing else interesting to see. But if you go lower in energy to the upper Hubbard band, then it changes. Then you see very different behavior. You see all this weird long wavelength modulations. You can see it with your eye. Look at the difference between these two images. They're very different. When we first saw this, we thought it was just noise or just some weird thing. My students were saying, what, we see this long wavelength stuff, and I thought it was just noise. But it's very reproducible. We see it all the time. And when you do a Fourier transform of it, you get very specific periodicities. You can see it here in the Fourier transform. I've circled the little dots in with these blue circles. We call it the ICS. That stands for incommensurate superstructure. And it's a long wavelength. You can see the wave vector is much shorter than the CDW wave vector, and we see it. We see it very reproducibly. And if we go down in energy to this region of the upper Hubbard band, we still see it. We take a Fourier transform. You can still see those ICS peaks. And if we go into the filled states, we see it also. Once again, you can see I've circled it in blue. You can see those features in the Fourier transform. But in the filled states, we also see an additional feature I've circled in green. We call it the CS, the commensurate superstructure. It's sitting at the K points of the Brillouin zone, and we call it commensurate because it is commensurate with the triangular lattice. Here's a zoom in of those images, so you can just see it a little better. You can see the ICS and the CS there. And when we saw this, we thought it was really weird. We didn't know where this incommensurate superstructure was coming from. But here we do some. Here I show some additional. Here I showed the average value of the ICS wave vector. If you average the data, then you can see that the wave vector of this incommensurate superstructure is 0.241 times the sum of the reciprocal lattice vector of the triangular lattice, which is the CDW lattice. This is just experimental. There's no theory here. It's just an experimental fact. If we look at the energy dependence of this feature, this ICS feature, then if we look at the energy dependence of the Fourier transform peak, we see that it's very strong near the Hubbard band edges here, but then it weakens as we move away from the Hubbard band edges. So it really likes to live in this Hubbard band edge region. Now, when we saw that behavior, we thought it was really weird. We thought maybe it was just some strange substrate effect because of silicon carbide lattice. There are weird reconstructions at the interface of silicon carbide and graphene. And we thought maybe it was due to that. And so we did the whole experiment all over again on HOPG graphite, which has no weird reconstructions. And we saw the same effects again. So here, when we grew the singular TSE2 on HOPG graphite, again, we see the ICS, the long wavelength modulations. But on graphite, we also saw an additional feature. On some of the islands, we saw this other long wavelength feature we call Q sub M, because this feature occurs at the M point of the Brillouin zone. That's these little middle dots. That's the M point of the Brillouin zone. So we saw this Q sub M. So the question then is, what are these long wavelength modulations? What is causing them? And so to make a long story short, we think that it's due to spin-on quantum interference. But before getting into all the fancy spin-on physics, let's first consider the conventional explanations. And so what is not explaining these long wavelength modulations? The first thing that comes to mind is electronic quasi-particle interference, QPI. QPI occurs when you have a scatterer that can scatter an electron from one state to another state with the same energy. And then the wave vector that connects these states, you can get quantum interference, which creates a standing wave at that wave vector. And so you can observe that. But this effect is very connected to the electronic structure of a material, and you can calculate it. And so when we calculate the predicted quasi-particle interference for 1T TSC2, which was done by our theoretical collaborators, then this is what you see. And you see that there's no features near the ICS wave vector or the M point of the Brillouin zone. And so we think that quasi-particle interference does not explain these results. Another possibility is that it's a moire pattern, but if you consider carefully the lattice constant of graphene compared to the lattice constant of TSC2, and you do the little twisty thing in your mind, then you'll see that you don't get these wave vectors. Also, because we did this experiment both on the silicon carbide and on the HOPG, we feel that's strong evidence against a moire pattern. So another possibility is that it's strain or some weird new charge density wave. And so we feel that there's evidence against this. For example, we do not see these long wavelength modulations in the lead, whereas we do see the Star of David in the lead. These features, these long wavelength features, are very weak outside of the Hubbard band, whereas the Star of David feature is very strong. If we warm the surface up to 77K, these long wavelength features, they go away, because the Star of David is still there. And we don't expect the strain to change significantly between 5 Kelvin and 77 Kelvin. Also, MBE of van der Waals materials is famous for creating very low strain films. We don't see any evidence of strain in these systems. So we think that these do not explain these long wavelength modulations. And so what we think does explain them is quantum interference of a spin-on Fermi surface. In fact, this explains the features quantitatively. And to understand that explanation, then let's consider once again what happens when we tunnel electrons into a quantum spin liquid. The rate at which the electrons tunnel is going to be proportional to the spin-on wave function times the charge-on wave function. And the energy of the electron that goes from the tip to the surface, which is E times V, is going to have to get divided between the spin-on and the charge-on, which get made when the electron goes inside of the quantum spin liquid. So if you bias your STM so that you're tunneling into the band edge of the Mott insulator, then, which is easy to do, then all the energy of your electron has to go into the charge-on, because it costs a lot of energy to make a charge-on. You have to overcome this energy gap. And then there's no energy left over for the spin-on. It's like, oh, no energy for the spin-on. He gets zero energy, but he still is there. And so to create a zero energy spin-on, then the spin-on has to be created at the Fermi surface, the spin-on Fermi surface. That's the zero energy for spin-ons. So what that means is that if we tunnel into the band edge of the Mott insulator, we are probing the spin-on Fermi surface, if it's a quantum spin liquid. So we can ask ourselves then, what do we expect the spin-on Fermi surface to look like for a quantum spin liquid on a triangular lattice? And luckily, there are some smart theorists who've been thinking about this for a while. And one of those theorists is Patrick Lee. And he and his coworkers have done some calculations using density matrix renormalization group theory on a triangular lattice for materials having the same parameters as 1T TASE2. And according to their predictions made a couple years ago, they predict that indeed you should have a quantum spin liquid on this triangular lattice. And they have calculated the wave vector of the Fermi surface of the spin-ons. And so here's the spin-on Fermi surface that they predict. And they predict that the wave vector, the Fermi wave vector, should be 0.375 times B, where B is the length of the reciprocal lattice vector of the triangular lattice. Furthermore, they predict that the spin susceptibility of this material should have peaks at 2 kF. And that's not surprising because anytime you have a Fermi surface, then the susceptibility always has peaks at 2 kF. That's very famous for charge density waves in normal materials. It's a famous thing in solid state physics. And so it's not surprising that they saw peaks in the spin susceptibility at 2 kF in their theory calculations. But what is surprising is that at certain directions in the Brillouin zone, they saw no peaks. The peaks went away. And so here I'm circling in black the regions where the peaks went away in the spin susceptibility according to their calculations. So the absence of a peak in the spin susceptibility suggests that the Fermi surface is missing in those directions. It suggests that the Fermi surface is gapped like that. See, I've made little gaps in the Fermi surface, and that's not a really surprising thing because Fermi surfaces are often partially gapped. That's many charge density wave systems show that. There are many things that can partially gap a metallic Fermi surface. Such as, and so here for the spin-ons, an example would be spin-on density waves, spin-on-spin density waves, spin-on pair density waves. All of these explanations can partially gap the spin-on Fermi surface. And I will add that all of these will lead to the same answer in the end. But there's one of these explanations that we feel is most likely for our system, and that is the spin-on pair density wave. So I'm going to just focus on this one possibility, and I'm going to explain how this happens and how it can explain our results. But I just want to add that all of these explanations will also lead to very similar results for the STM. So,
Mike, sorry.
Yeah.
There's another question by Dennis. Dennis, please go ahead.
So no, I'm just wondering what defines the size of the Spinon Fermi surface compared to the Brilliant zone size? What is this factor given by?
Well, it's really kind of simple because it's like here, if we look at it, we just have one spin per unit cell. And so from just simple counting, it's just like a free electron gas, because if I have one electron per unit cell in a free electron gas, then I expect the Fermi surface to be half the size of the Brillouin zone, the area. And so here it's the same thing. We have one spin per unit cell, so that means we have one spin-on per unit cell. So that means that we expect the Fermi surface size to be half the Brillouin zone. And because it's like a free electron gas, we just expect it to be a circle in the middle of the Brillouin zone. But it gets slightly distorted. Yeah,
okay.
Does that answer? Yeah. Okay.
Yeah, it's very simple. Thank you.
Yeah. Okay, so what we think is causing the partial gapping of the Fermi surface is a spin-on pair density wave. Okay, so what is a pair density wave? A pair density wave is basically just a Cooper pair that has finite momentum. So here we're talking about spin-on, so it's a spin-on Cooper pair with finite momentum. And so the idea is that if I have two spin-ons here at the Fermi wave vector, then if they attract each other and gap out and form a Cooper pair, then you lose the Fermi surface to that region and you gain a pair density wave, a finite momentum Cooper pair. But spin-ons are neutral, so you might wonder, why would they attract each other? It kind of doesn't make sense. But it turns out that there is a mechanism that can cause that. It's called Amperian coupling between spin-ons. And what's happening is that even though the spin-ons are neutral to us, to each other, they can feel gauge interactions. So if one spin-on is moving with some velocity, you can think of it as creating a current because it has a gauge charge, and that creates a gauge field, a gauge magnetic field that other spin-ons can feel. And so we can think of these two spin-ons as basically being two wires carrying current. And from introductory physics, we know that if we have two parallel wires carrying current, they are attracted to each other. And so that's the attraction that could then cause these two spin-ons to gap out and form a pair density wave. And people have written papers on this, as you see down here. And so that means that if those two guys gap out and form a pair density wave, even though they are removed from the Fermi surface, they are still there. But now they have big momentum because there's two spin-ons. So now the momentum of that pair density wave is 2kF. Now that's a pretty big momentum, and so if we consider that pair density wave, the momentum is so big that it pops it right outside of the Brillouin zone, as you see here. But we all know from basic condensed matter physics reasoning that if my crystal momentum is outside of the Brillouin zone, then I can always bring it back into the Brillouin zone through band folding by simply adding a reciprocal lattice vector. So here I add a reciprocal lattice vector, this green arrow, and I pull that crystal momentum back into the Brillouin zone. And so now I get this vector P. P stands for primary. And so this is the crystal momentum of the pair density wave in the Brillouin zone. But because this is happening at 6 different momenta, we expect the pair density wave, if it gets scattered, to have components in these 6 different directions. So we expect from simple symmetry reasoning, we expect the pair density wave function to have components at these 6 different directions. So then we can ask the question, what is the state density of the pair density wave? To answer that question, all we got to do is square it. And so if we square it, then we see that these 6 waves get squared. And when you square the waves, what you get are the second harmonics. So here I show the second harmonics of these P vectors, and those are these blue dots. And this is very simple. There's no fancy physics here. I'm just squaring the waves. You could do this with a pad and pencil in 5 minutes, and you get the second harmonics, these blue dots. And this is a and so this is basically these are the standing waves that we expect to exist in the paired density wave function. And this is a quantitative prediction, because remember, the density matrix renormalization group theory predicts that the Fermi wave vector should be 0.375 times b, the reciprocal lattice vector. And so all of this started from the Fermi wave vector. And so that means that if we just follow this reasoning through, then we have specific predictions, specific quantitative predictions for the second harmonic, these blue dots. So we expect them to exist at 0.249 times b1 plus b2, where b1 and b2 are the reciprocal lattice vectors of the triangular lattice, and also at 0.5 times b. So those are the predictions for the paired density wave.
So, sorry, Mike, there's a question from Thomas.
Hi.
Sure.
Hi. Maybe you explained this, but I probably missed it. So why the pairing is happening along the gamma m direction? Could you please explain?
Okay, that's a good question. The simple answer is we don't know. But now I'll give you the longer answer. The longer answer is that this is something that comes out of the density matrix renormalization group theory. So you do the calculation and boom, it just comes out. This is my understanding, at least. And so we're not exactly sure. However, we do expect the density of states to be slightly bigger in the gamma m direction, but based on some simple reasoning. We expect the density of states to be bigger. And so we think that that might then enhance the effect in those directions, but we're not sure. but it does come out of the density matrix renormalization group theory calculation.
Thank you.
Okay. Okay, so this then is so then from this Fermi surface instability, we expect to see these standing waves in the paired density wave, and so we expect to basically get a grid of state density of the paired density wave, as you see here in this simple cartoon. But the problem is we cannot see the paired density wave, because when we tunnel electrons into a quantum spin liquid, it creates a single spinon. It does not create a spin-on pair. so this thing is invisible to us. But it's not invisible to the spinons, because don't forget, the spinons are still there. The spin-on Fermi surface is still there. Even though it's partially gapped, there are spinons swimming around. And those spinons feel the paired density wave, and they're going to scatter off of it because they feel it through the gauge interaction. And so we expect scattering of the spinons. In fact, the paired density wave creates scattering at these wave vectors. These are the wave vectors of the standing wave of the paired density wave. And so if those wave vectors can connect two states having the same energy in the spin-on electronic structure, then we expect quantum interference in the spinons at precisely those wave vectors. And from just simple geometric argument, if you take these paired density wave vectors and you bring it here, you can see that indeed they do connect energy conserving states in the spin-on electronic structure all over the place. So we expect lots of spin-on scattering channels at these wave vectors, and which means that we expect spin-on quantum interference, spin-on quasi-particle interference at those wave vectors. And that's what we can see, because that quantum interference should show up in the wave function of the spin-ons, and that's what we can see with the STM. So all of this reasoning then leads to some very specific theoretical predictions of what wave vectors we should see with the STM, and these are the predictions that you get, because from the density matrix renormalization group theory, we have a prediction of the Fermi wave vector here, 0.375b, and that leads to these specific predictions of the wave vectors that we should see in the quantum interference of the spinons. The prediction is that we should see wave vectors at 0.249 times b1 plus b2 and 0.5 times b. So these are the predictions, and now let's look at the data. And this is the data. This is what we see experimentally. The agreement is strong. Here in our data, you see that we see quantum interference at precisely these exact wave vectors that's predicted from the quantum spin liquid picture. We see wave vectors at 0.24 b1 plus b2 and at 0.5 times b. The agreement is striking, and when you and so we can take our data and work backwards, and then extract the Fermi wave vector of the spin-on Fermi surface, and when we do that, we get 0.370 times b, the reciprocal vector, which we can compare to the theory, and the comparison is quite strong. So that's my story. That's the end, but I'll just mention some open questions. These are the weak points of the story, and so if you can't think of anything to ask me, you can ask me about these. The weak points is, what about the commensurate superstructure that I showed you before? I swept that under the rug. That's the one that occurred at the K points, and the reason I swept that under the rug is because the quantum and liquid cannot explain that cannot get that periodicity from the quantum spin liquid, but we can get it from the 120-degree Néel state. And so we think that local fluctuations might explain that. Also, where are the P vectors, these red vectors? We don't see those. And from the reasoning I have given you, we should see them, but we don't. We think that might be explained as by a structure factor, but that's an open question. And also the last one is, where are the Spinon-Friedel oscillations? What I've been talking about today are not Friedel oscillations. However, using similar reasoning, you would expect to see Friedel oscillations, which we do not see yet. It might be because our energy resolution is not good enough. So to conclude, we have measured the Fermi wave vector for a gapless quantum spin liquid on a triangular lattice. It agrees quite nicely with theory. And for the future, there's a lot of stuff to do that as soon as we can get back into the lab, we'll hopefully do. We haven't been working on this for a long time because of the stupid virus. Here are my collaborators and funding agents. Lots of people collaborated to do this work, funded by DOE and NSF. All these people contributed a lot, but I do want to call out a couple of names. The people in my laboratory who led the STM work are Wei Ruan, Yi Chen, and Ryan Lee. They took all the STM data that I showed today. Thank you.
Thanks a lot, Mike, for this very nice and very interesting talk. So now we have some time for questions, and for that you can use the participants button and press the raise hand button. And
we already have one, I think.
Yes, yes. So
Alex, go ahead.
Hey, Mike. Alex here. I have two basic questions I didn't completely follow. So one is, does the orbital moment of the tantalum play any role in defining the spin? And the second one would be, like, how robust is this quantum spin liquid state to this disorder, maybe the defect density, for example, in the film?
Okay, first the tantalum. Let me try to remember the the crystal field splitting and all that of the tantalum. I think that I think the answer is that the orbital does not play a role. I think that there's some splitting of the. I mean, if you actually wait, I have my periodic table right here. I mean, if I look at tantalum, where the hell is tantalum? Tantalum. Oh yeah, there it is. Yeah, it's 5d3 6s2, and the selenium. So that means there's 5 electrons there, 3d electrons and 2 s electrons, and the selenium sucks away 4 electrons. So the selenium sucks away 4 electrons. So there's only 1 electron left, and that electron is in the d orbital side. I don't think the orbital plays a big role here. And then your next question is a question about the disorder. And I don't know. That's a good question. You know, the disorder. I don't have a good answer to that. I don't know the degree to which it's stable against disorder. I think that's a really interesting question. That's something that we would like to study.
There's another question by Sander. Sander, please go ahead.
Thank you, Mike. Great talk. Thank you. So you showed that the actual lattice for your mod insulator is quite big, right? So there's these stars of David. And that means that your spins in your quantum spin liquid are quite far apart. And in order to get a quantum spin liquid, you need them to still couple quite strongly to form singlets. So what is the mechanism by which they couple over such a long distance? It cannot be just wave function overlap. So can you say something about that?
Yeah. That's a good question. I mean, we think experimentally, we think, I mean, we can put some limits on the J, you know. We think that the J coupling between those local moments is not so strong because the Kondo can overcome it, and the Kondo has a Kondo temperature of 60 Kelvin. Now, you have, the thing is, we're emphasizing that the spin is coming from that central atom of the Star of David, but actually, if you look at the details, it's really, this is not a single band mod insulator. It's a multi-band picture because we really have the whole Star of David, and so there's going to be still some components of those peripheral atoms. I kind of brushed that under the rug, you know, to not get into all that complexity, but there will still be some component. There will still be some mixing of those different atoms in the Star of David, and so I think that there will still be some there could still be some wave function couplings between those central atoms from one central atom to the other. So I believe that there is a wave function exchange coupling between the different central atoms, but it might be mediated by the peripheral atoms of the Star of David. But that's not something that we have actually calculated. That's only my own personal intuition. So that's sort of the best I can do to answer your question.
Okay, thanks.
There's another question by Liwo. Liwo, please go ahead.
I cannot hear.
Liwo, you can ask your question.
Hello, Professor Mike. Excellent talk. I have a question for the pair density wave you mentioned in the slides. So it's a triplet or it's a singlet. I just mentioned it's whether it's similar to the Magnon waves.
Okay. Yeah. Patrick Lee has studied it and has, there are some papers on it, and I think that in Patrick Lee's paper, he suggests that it is most likely a singlet, but there is also a possibility that it's a triplet. And so I think that there is not a firm rule that it has to be either singlet or triplet. I think for the parameter regime that Patrick Lee used in his calculations, he suggests that it is a singlet. But if you slightly tweak the parameter regimes, I think that you could also get a triplet. That's to the best of my knowledge. I mean, I have to admit, I'm not a big expert on that theory, but I think those are some statements that he has made in his papers. And what was the rest of your question? I forgot.
That's it. Yeah, thank you.
Okay.
Next one from Daniel.
Yeah, hi Mike, can you hear me?
Yeah. Oh, hey, hi. Hi, Daniel. You look the same. You haven't changed.
Yeah. I got two questions, a physical one and a more technical one. So the physical one first, what would happen if you apply a magnetic field to your quantum spin liquid, or what order of magnitude does the field have to have in order to see some effects on this experiment? And then the technical one, I would be curious, how do you transfer the sample from that MBE system, which I suppose is somewhere up on the hill or so, to your LTSTM? How do you do that?
Okay, so the magnetic field question. So up to now, the only magnetic field we have is one of those Createch magnetic fields, for the 4K machine. And so, and they're supposed to work up at 3 Tesla, but if you crank it up to 3 Tesla, then the machine goes bang and hits the side. It doesn't work. And so we can only go up to 1 Tesla. And so we turned it up to 1 Tesla and saw nothing. Okay, no effect at 1 Tesla. And that's not so surprising because, the question is, it goes back to this question of what is that J coupling between the spins in the 1T TSE2? And we don't know what that J coupling is exactly. I would say that the Kondo temperature puts an upper bound on the J coupling of 5 millivolts, although that upper bound is squishy. But even if we put an upper bound, at a few millivolts, then that means that basically the magnetic field has to break that. We need a magnetic field that can break that J coupling. And so I would say if the magnetic field can overcome that J coupling of a few millivolts, then it should start killing the quantum spin liquid and polarizing the electron. So that's the magnetic field that we need. So and you know what that is, right? A couple of millivolts is a few tens of Tesla. And then the second question is the transfer. The data that I showed you, we did selenium capping. That's the answer. So we did selenium capping. So they grew the films up on the hill at LBNL and they capped them with selenium and we brought them down and we blew off the selenium in the UHV and it worked pretty well. The capping doesn't always work for every material, but for this material it worked pretty well. Lately we've been doing vacuum suitcase. So I think we've done some measurements with vacuum suitcase, but the selenium capping works pretty well for this system.
Okay, thank you.
All right, Leo next.
Hi, Mike. Thanks for the great talk. My question is about so this David stars of David. So they seem to be fixed. So you have really, on which atom you have the single spin and or a single electron. So what determines where this David star sits? Is this a boundary condition of your flake, or is it some spontaneous symmetry breaking?
That's a good question. I mean, like, well, first I will say that it's commensurate. So the David star has to sit on a tantalum atom. It has to sit, you know, at the center of the David star has to be a tantalum atom because it's a commensurate CDW.
Sure, but why not one of the other 12?
Yeah, it's a good question. I mean, I assume that there must be some boundary condition that picks one, and then all the others then are picked. I assume. That's an interesting question. I've actually never even thought of that until this moment. And so that's what I assume happens. I assume that, you know, at some point, you know, the CDW has to nucleate somewhere, right? I mean, because when you're growing the film at, I mean, we blow off the selenium at high temperature, and then as we cool down, the CDW sets in, and I forget the number, but it's like, you know, probably 400 Kelvin is when the CDW occurs. So as you cool down from the growth or from blowing off the selenium, the CDW has to nucleate somewhere. And so I assume it just nucleates somewhere based on the boundary conditions and then just spreads. I assume that happens, but it's not something I've ever really thought about. I know that in the TAS2, it gets more complicated because you can have incommensurate CDWs, but we're not in that complicated regime. We have a commensurate CDW in this case.
Thanks.
Wander?
Yeah, so I have a quick related question. Actually, I stared at the lattice for a while, and if you look closely, the CDW can actually form a clockwise lattice or an anti-clockwise. So it's not only just 1 out of 13 atoms where the center of the David star can sit, but they can also form in 2 different ways. So it would be interesting to see at some point if you can also observe the counterclockwise or the clockwise version of the CDW. But that's just a side remark.
Oh, thank you. I've never thought of that before. Okay. That's interesting. Okay. Yeah, I never heard of that before. That's kind of cool.
There's another question by Dennis. Dennis, please go ahead.
Mike, you have mentioned that 1T tantalum disulfide is also a similar material, which is bulk insulator if you go to a thick limit. I'm just wondering, what was your choice? Why did you choose to work with tantalum selenide rather than tantalum disulfide? And have you tried the second one as well?
Yeah, that's a good question. I mean, first I should say that my motivation for doing this experiment was I visited Patrick Lee, and Patrick Lee said, Mike, get rid of the interlayer coupling. Look at tantalum disulfide in single layer. And so I went, oh, okay, let's do tantalum disulfide. But then when we talked to our growers, they hate sulfur. Most MBE guys hate sulfur because it contaminates their chamber. And whereas selenium is really nice for MBE guys. They love selenium. And so that's basically the reason why we did TASC2 instead of TAS2. I wanted to do TAS2 instead. Now, in the meantime, Chi-Kun Shui's group has done some TAS2. So their Chi-Kun Shui's group has done single layer TAS2. Those guys are, they're quite amazing. They're fabulous MBE guys, and so they have done some TAS2. But with the TAS2, they've seen some slight differences. I don't know that they, these long wavelength modulations are sort of, not obvious at first, so I don't know if they've, I don't know the degree to which my group has not looked at the TAS2, and I don't know the degree to which the Chi-Kun Shui group has looked for these long wavelength modulations.
Thank you.
Wei Yong, go ahead.
Hi, a very good talk. Maybe I have some misunderstanding. I don't understand where you can see the Fermi surface, of the Spinon, because usually for electrons, STM can see the Fermi surface from using QPI. We can't directly see the Fermi surface of the electrons. So how can we directly see the Fermi surface of Spinon?
Okay, well, I would say that the argument is really the same. because when we see the Fermi surface for the electron material, we're seeing it through the QPI, as you just said. And
Yes.
so the idea here is really exactly the same, because here we're seeing the QPI of the spin-on surface here, but the scattering, what we're scattering off of is a diffraction grid, and so it is exactly the same argument. So
okay, I see.
It is exactly
so
the
it's
same
already is the Friday oscillation of the spinon. Okay.
Yeah, but I won't say, I hesitate to use the word Friedel, because that's like a very specific thing, because for Friedel, you're integrating from the bottom of the band to the top of the band, and you're seeing the 2KF. I would say this is more general than that. We're just basically seeing the QPI
and also,
these wave vectors.
And I also feel, also this slides, because you can see your Fermi surface is, though your Fermi surface is not a circle, it's also a continuous Fermi surface. So why you just see some specific scattering point?
Why do we see these specific ones? Well, the reason is because the spin-ons, which are free to move on this Fermi surface, are scattered off of these wave vectors. This is what's scattering them. So you can think of the pair density wave as basically, we have standing waves. The PDW is creating standing waves. It's like a diffraction grid. And so the spin-ons, which are free to move like free electrons, are bouncing off this diffraction grid. And so they will then be scattered at the specific wave vectors that define the
I
diffraction grid.
understand. For example, for QM, if it's a little longer, and move to the right side, it can be longer to the in the spinon scattering channels. This image.
Yes, but there is no scattering potential that. There's no scattering potential creating a Q sub m that's a little bit longer. That scattering potential does not exist.
Okay. See. Thanks.
Okay.
Let's take one more question from Willem.
Yep. Hi. So I would like to ask you, in the beginning, you showed the difference between measured local density of states and calculated from the DFT plus U on the Hubbard bands. And in the end, you basically claim that you know quite a bit about your spinons, and you claim there are Gapless and you know their Fermi surface. So could you basically, case works, reconstruct the STM data that you showed? Yeah.
So I guess I don't exactly you're asking, can we reconstruct the STM data? Yeah. What do you mean?
Well,
exactly?
based on the knowledge of your spinons, that I mean, there was this difference between the STM data. Yeah.
Okay, well, I guess I'm not exactly sure how to answer your question, but what I'll say is, and you can tell me whether this is getting at what you're asking. I mean,
so in case you include the spinons and the spinon Fermi surface, so could you reconstruct it?
Well, I mean, in some sense, let's see.
Well, there was this specific value where it was different, the STM data and DFT.
For the upper Hubbard band. Okay, yeah. So I guess what I'm doing is I'm showing two different theories here in this talk. On the one hand, I'm showing this DFT plus U, which is helping get at sort of the specific electronic structure of my material. But then I'm showing this more idealized density matrix renormalization group theory result right here on the slide, which is trying to get at the spin-on physics. And so it's two different theories. And I think you're asking, can we combine the theory into one unified whole? Is that what you're asking?
Yeah.
And I would say the answer, yeah.
Expected. And then
I would say,
yeah.
The problem, okay, here's the problem. There's two problems, I would say. The first problem is that the DFT plus U is only an approximate. It's really hard to calculate a Mott insulator. There's no good technique to do ab initio calculations of a Mott insulator. It just doesn't exist. I mean, you have this dynamical mean field theory, but my understanding is you can't even get LDOS from that. So there's no good ab initio theory. So we do the best we can, which is the DFT plus U, in our opinion, for us. that's one problem. But then another problem is that when you talk about this kind of quasi-particle interference behavior, it's really hard to get at that using an ab initio technique because the unit cells are so big. So I don't think any ab initio people can really, calculate this type of long wavelength quantum interference because the unit cell is so gigantic. This interference is living inside of you see it's long wavelength, it's inside the Brillouin zone. So to really calculate this using an ab initio technique, you would need to first be able to calculate all the correlation effects in the ab initio technique, which can't be done. And then you would have to have a gigantic unit cell, which can't be done. So it's really hard to have a single unified theory that can give you all of this. It's just basically beyond the current theoretical capabilities.
Okay, maybe we didn't understand.
Yeah. Okay. What I would suggest at this stage, I know there are more questions, so don't despair. What I would suggest at this stage is that we stop the sort of official part of the talk, we stop the recording, and then those of us who still want to ask more questions, we can stay online and do that. But let's thank Mike once more, and stop the official part of the talk. So thanks a lot, it's really great.